Okay, so we will start by discussing and proving conformal invariance for two related models, which are the uniform spanning tree and the loop arrest random walk. So I will come to the other one in a quarter of an hour. So I won't do everything rigorously. I would rather try to emphasize ideas, and then other models will do more rigorously. So this is one of very old models, and in a sense it works nicer than the other ones. Essentially it appears already in the work of Kirchhoff on electrical networks. So what we do, we take a graph. So were they discussed in one of the previous courses? Uniform spanning trees? Yes, not. Sorry.
On Werner's course.
On Werner's course. Okay.
It was not on the course, more on exercise.
Yeah. Okay. So I will just briefly say a few things, and then maybe I'll prove some, or maybe I'll put some in the exercise. So we take a graph G. Connected graph, yeah. For example, part of a domain in the square lattice. Yeah, so something like this. And then we can take, consider all connected, well, let's say, minimal connected subgraphs. Now, what does it mean that the graph is connected? Well, subgraph is connected. Yeah, maybe I poorly worded it. So maybe, so we, if I, for example, this would be a disconnected subgraph, obviously, because there are 1, 2, 3, 4 components of connectivity. So if it's, so I need to add some edges. Now this graph is connected, but it's no longer minimal because it has cycles. So I can, for example, delete this edge, and it still is connected. So minimal connected, basically, it means it's that minimal connected is the same as that it's a covering tree. It's a tree which covers all vertices. So this is what is called a spanning tree. So we consider all possible spanning trees. So all possible trees which cover all vertices. For example, this is a thing. So say if we have a graph path of 4 vertices, then obviously there are 4 ways to do it. That will be like that, like this, and like that. So we just, there is one cycle, so you only have to delete one edge. And obviously all of them will have the same number of edges. They will have just one edge less than the number of vertices. So if you have one vertex, you don't need any edges to connect. If you have 2, you need 1 to connect, and so on by induction. Uniform spanning tree is so UST is a random model where a spanning tree is picked uniformly at random. So basically, so here each one of them has probability 1/4 to be chosen. So obviously one can do not necessarily uniform things. So the most usual thing people do is assign some weights to edges and weighting this graph by product of weights of edges. So so there are several things, several remarks which I want to make. So the first remark is that it basically dates to Kirchhoff's book. So it's like 1847 something. It's relation to electrical networks. So he observed that if you have, for example, that you say that this white graph is an electrical network, and you want to calculate current flowing through some edge. Well, for example, if you take an edge and you put you apply a battery to it, so you have potential difference of 1 between the edge ends, and you ask what current will flow through it. I mean, it's not one edge, it's the whole graph, so part of this current will go through other edges. So this can be calculated through the number of the spanning trees which have this edge in them. So this is one of the examples. So we'll come to this later. Now, and that sort of makes it more easy than other models. So he also observed that this is related to random walk. Well, he didn't directly write relation to random walk, but he did directly write relation to Laplacian. So basically, now I always mess it up. So someone who knows corrects me. So the number of spanning trees on a graph is equal to, so you take Laplacian on the graph, the discrete Laplacian, and you take product of all its eigenvalues, lambda j. Now, you cannot take product of all the eigenvalues because the first eigenvalue will be 0, because there is a harmonic function which is constant. So you start from the second one, and then you had divide by the number of vertices. So it's either this or the other way around. Yeah, it is this, yeah, I think. Yes, yeah, sure. Well, there are several reasons why it is this. It's just, it's also, you know, I mean, my problem is that it's like sort of breaking your egg from the obtuse end or sharp end, where the Laplacian is Laplacian or minus Laplacian, and then of course there is a question of sign here. Alternatively, you can write it as the determinant of the adjacency matrix. So you take let me say now. Okay, so it's determinant of the matrix A, where Aij is equal to degree of vertex I. If I is equal to j, it's equal to -1 if there is an edge ij, and it's equal to 0 otherwise. Now here I might have confused the sign, but I don't think I did. So this is basically Laplacian matrix, and that's more or less the same formula you get.
No, it equals 0, yes.
Sorry?
It equals 0 now.
Let me see. I think I was careful enough. Does it?
So you have to erase one row.
Yeah, I have to erase one row. Yeah, I have to erase one row because, for example, if yeah, you just erase anything. Yeah, just erase one row. So it's determinant A. Well, let me just sort of do well with row erased. Yeah. So that's not really important for our purposes, but this is actually indicates that the model is easier. There is a third thing which I don't want to do. So you probably heard Young-Baxter relation or star triangle transformation. So so this is one of a very few models. One of, well, there are actually three only. One of a few models. Very friendly, which are very friendly to star triangle transformation. Or also it's called Young-Baxter. So what is the star triangle transformation? Is that you have some graph G, and you have somewhere three vertices which form a triangle, and then you take to a different graph G prime where you connect them instead by a star, and everything else is just the same. So what is the nice thing about electrical networks, so uniform spanning trees, is that if you have three resistors on the edges of this triangle, you can always find three resistors here of some resistances which are functions of those, that this configuration will behave exactly the same in the network. And the same goes for uniform spanning trees. If you do weighted uniform spanning trees, for any weights here, you can pick up any weights there. So what is the difference? So we are not discussing in our course Young-Baxter approach to lattice models. So all like Potts model, so Ising model can be approached, but this property that for any three resistances you can find three resistances here, it's only enjoyed by electrical networks and the Ising model. For other models there is a restriction. For Potts model, if I put here some three arbitrary resistances a priori, you cannot do this change. There is a one condition on them, and then somehow restricts what that method does on this model. Now, yeah, that's the remark 4, is that we can count edges with weights. So in the electrical networks, resistances in electrical networks. So, by the way, if you haven't seen this theorem, it's a nice exercise to prove. There are several ways to do it. It's not, well, obviously it's not easy, but it's much easier to prove it knowing that it is true than discovering this relation. So it's, for example, how one of the sort of obvious but not the easiest ways how to do it, the way how one can analyze spanning trees or drawing spanning trees is by induction. So spanning trees can be studied by induction. So what you do, you start with a graph G and you pick some edge E. And then there are two possibilities. Either edge E belongs to the spanning tree or it doesn't belong to the spanning tree. So there are two possibilities. So E belongs to spanning tree, E doesn't belong to spanning tree. If it doesn't belong to spanning tree, then you can just, your spanning tree is a spanning tree in the graph which is the same, only there is no this edge. Then so for example, you have spanning tree in G, then here you have to study spanning tree in G minus the edge E. Now, if the edge E belongs to the spanning tree, then what you can do, you can contract it. You can just fuse these two vertices. And your spanning tree, this is spanning tree in G with E fused. So you just sort of, these two vertices you glue together. So it's one vertex less. So each time either you erase one edge or you fuse two vertices, there is one vertex less. So by induction, eventually you arrive to trivial graph. And this is sort of the easiest way to implement a computer, and this is actually a way to prove some of the theorems. You can prove all the theorems about Laplacian in that way too, though it's maybe not the best one. Now there is a relation to domino tilings, to dimer models. Now, this hasn't been mentioned by David yet, no? No. Okay, so I will do the following. I will draw a picture. It's like this saying which is attributed to Napoleon that one picture is better than 10,000 words, but it's actually, I think he never said it. It's more about this graphic which shows how his army deteriorated during the winter. I'll draw a picture which shows the relation to dimer models. It works for any graph, but it's sort of less for any planar graph, so it's a relation to dimer models. So for example, what you have is that UST on square lattice is related to domino tilings. So there is a bijection between UST on region of a square lattice to domino tiling of a related region. Unfortunately, that's the reason why it's difficult for other graph. It's not that you take a region of a lattice and you take another region of the same lattice. You have a related region of a different lattice. In square lattice case, it's just a lattice which is which has twice bigger step. So I will draw a bijection. So let me see. So this is 1, 2, 3, 4, 5. Yeah, okay, let's do 5 by 5. So this is an example of the region for which it works. So this is you take the domino tiling here. And the related graph where you take the UST is this graph. So domino tiling of white graph is the UST on this blue graph. So this is called temporally bijection. And basically it says that if I draw a domain on a blue square lattice, I can draw a white domain on this lattice, which is called temporally domain. So you see that this domain, all its corners are blue. So it's maybe so that it's less trivial. Let me draw it for such piece of a graph. Then for such piece of a graph, it would be like that. Yeah, so this is more general example. This basically explains what you do always. And then you chew off one corner of it, because otherwise it's an odd domain, so you don't have dimer tiling. And then there is a bijection between UST here and dimer there. So I will just draw it. So suppose we have a domino tiling of a domain. So let me draw some domino tiling. So how do I do it? One domino, another 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 one, another one. Okay. Now, as you noticed, every blue vertex is covered by a domino. So we draw an arrow for the domino which covers the blue vertex. Not all the dominoes cover blue vertex, but every does. So we can draw these arrows here. I can move them. So I just move the blue arrows here. And now, oh gosh, what have I done? So I've done the most trivial example. So now I just take the edges where I have drawn the arrows, and I get a uniform spanning tree. In my case, I got a trivial tree which has no branches, so it's maybe not so much fun. But that was a pure coincidence. I don't know why I did it. Let me do something more interesting. Let me do, for example, this spanning tree, and we'll see how it changes. So that in this case it's drawn here, in this case so it's drawn here, so you have a genuine tree with one branch. So basically let's do this as an exercise. So it's exercise 2. So this is, let's say, I don't want to put it as an exercise. I will write anyway that it's exercise 1, but some of you have seen it. There are several proofs of it, and it's not enormously difficult. If you know the theorem, you can do it by induction. Now this is very easy. So basically, I outlined the proof that. What happens here, you have to check that you get a tree when you draw these arrows. What is a possible abstraction to not getting a tree is that you get a cycle. Because what you have the number of edges you draw is exactly one less than the number of vertices, because there is one vertex where you don't draw an edge. So if you have drawn a tree, it will cover everything. So if you have no cycles, then it will cover everything, because you have exactly say 100 vertices and 99 edges. Then it covers everything, it's connected, unless it has a cycle. Now, if it has a cycle, so let's, for example, look at the simplest possible cycle, which goes like this. Then you can easily see that inside there is a one cell which is not covered by any domino. So basically that's the bad thing, that if you have a cycle, you can calculate that it will surround an odd number of cells, and you get a contradiction because whatever is inside the cycle should be covered by dominoes. So that's the contradiction. The other way around is also easy. So if I draw here a tree, I take this root. And then on the tree, there is a unique way to put arrows how to go to the root, because in every tree, there is a unique way to the root without backtracking. So I put arrows so that I go to the root. So this is one way, this is another way. And then for every arrow, I put here a domino. So I get a collection of dominoes which cover all the blue cells and all the blue edges. And then you have to check that the complement is also uniquely covered by domino. And actually the complement is also a uniform spanning tree in its own right, so that we'll be using later. So the complement you can also do as a uniform spanning tree on a dual graph. So the complement looks like that. So the complement is also uniform spanning tree on a dual graph, so the complement is the spanning tree which has a root nearby. So in principle, you can also do this procedure not on the blue graph, but rather on whatever color that is, and you get your bijection. But once again, this bijection, for if you start with a uniform spanning tree, you can start with any graph, and there is a way to produce graph here. If you start with a domino tiling, it should be a special graph which has certain parity properties, and then the uniform spanning tree graph will be twice small, so to say. Okay, so that's another relation. Now, the question, of course, which arises after all that is that how, for example, if you want to study them, how you generate them. And the very surprise, so how you draw them on a computer, uniform spanning trees. Obviously, you can do this, you can just try doing the full search, but that would really take a very long time. I mean, it's clear from this Laplacian formula, and there is also different calculations of diameters. It's clear that the number of spanning trees is exponential, some exponential of the volume. So if it's n by n domain, it's exponential of n squared. For a long time, the main algorithm was Bruder-Aldous algorithm, which basically what you do, you run random walk on your graph until it covers everything. And then what you do, each time some vertex visited first, you add edge to this vertex. So basically, when you make the first step, you put this edge because this is the first time you visited this vertex. You make another step, you put this edge. If you visit something you already visited, you don't. But then you come, go around what you visited. Once in a while, you step outside, then you add this edge. So the problem with this thing is that the running time is till you visit all the vertices at least once. But there is a small probability that there will be a few vertices which you don't visit for very long time. And then what happened is that David Wilson came up with a very nice algorithm. It's essentially a byproduct of his PhD thesis, and it's actually it's a particular case of a very nice way to sample Markov chains. So it's actually allows you to sample Markov chains when you don't know transition probabilities. So I will just formulate the Wilson's algorithm, but before I need to say what is a loop-raised random walk. So let's say loop-raised random walk. So loop-raised random walk is a random walk where all loops are erased. So that's exactly what it is called. So what you do, you take a graph. So that was introduced by Greg Lawler, and if you have been to his talk, you have heard some about it, as an alternative to self-avoiding walk. Now, self-avoiding walk, you take all simple walks with equal probability. It's not a Markovian model, as I said, because it very much depends. You can't really draw it from A to B with some kind of Markovian property, because how many ways to continue will very much depend on what you have drawn so far. For example, you can corner yourself so that there are no steps to be made, and then you are dead. Greg wanted to suggest some alternative thing, which is easier to study, but in the same universality class. So what he came up with is very nice. It turned out in the end to be in a different universality class, but it's nice in its own right. So it turned out to be in the same universality class as the uniform spanning tree. So basically, you take a graph G, run random walk. So for example, you can run from A till it reaches B. Then erase loops chronologically. So what do I mean? I mean that that you start running your walk, random walk, then it touches itself. Then what you do, you erase this loop. You continue. It goes, goes, goes. It intersects this that I don't care because this loop is already erased. It touches this. Then you erase that one. You continue. And so on. You hit B. That's it. So it's not a symmetric procedure. So if you run it from A to B or from B to A, if you draw the same curve, when you run it, well, in this picture it is symmetric, but let me just draw, well, let's draw some more complicated picture. So what do we get here? So we are drawing, and here we have to loop erase. So that we don't count, we only count, so this part stays. Then we are drawing. So far so good. And then we have to loop erase this part, so we are left with this one. And then we go. We loop erase this. Yeah, so this one. Yeah, again I got the symmetric one. Yeah, so it's I should have thought a bit more. So it's yeah. Will that work? Yeah, that will work. That will work. So that will work because if I go like that, so I loop erase this, so then I get this one. I go this. I loop erase this, and then I go. I go like that. Yeah. If I go the other way around, I go like this. So this part is loop erased. So I only left with this one. Then I go like this. This part is loop erased. I'm erased with this one, and then yeah. Okay. So yellow and blue are different. Yeah. So the remark is that we get a simple curve. Procedure not symmetric. And now what happened is that, so this is, well, maybe one of the reasons why this UST algorithm came up late, because loop erased random walk was introduced very late. So that was late 70s, I think, or early 80s when Greg introduced it. And then what was observed first by Pemantle, it's a simple version of Wilson's algorithm. It was a connection between loop erased random walk and uniform spanning tree, which show that actually it is symmetric. So the procedure is not symmetric, but the curve you get is symmetric. So well, let's say lemma. So this is due by Pemantle, and then it was superseded by Wilson's algorithm. Is that UST branch is the same as a loop erased random walk. So what do I mean? UST branch from A to B. So if I draw uniform spanning tree and I take 2 points A and B, there is always a unique curve joining them. Because it has no loops, there is a unique curve joining them. So there is a unique branch of AST joining A to B. It's the same as loop erased random walk from A to B. Now UST branch doesn't distinguish between two endpoints, so you just fix 2 points and you ask for unique branch. So it means that loop erased random walk from A to B is the same as from B to A. So that sort of implies that loop erased random walk AB is equal to loop erased random walk BA. So the ways how they constructed are different. I'm speaking about loop erased random walk. Oh, there are better people who can speak about it. Then go. So then it gives that it is symmetric. So it's in a sense it's a surprising result because from the procedure it's absolutely not clear why it should be true. And then, so this is again, this is a kind of a lemma that I don't know how people arrive at this lemma. But once you know it is true, since it's an identity, it's not difficult to prove. There are several proofs. Well, you can do it by induction. It's not the correct way to do, but this sort of contracting of a graph is a possible way to do it. You can also do it through Laplacian and all these Max-Cut theorems. So maybe we'll do it as a exercise 3. So by exercise, so this is indeed, it's just easy exercise, just think about it. So this is the first one is a complicated one. So we'll either work through it on the next lecture or well, maybe we'll split it into small blocks and put it in the homework assignment. Now, what is the Wilson algorithm? So Wilson's algorithm does the following thing. So you take a graph G. Take points A, well, let's say A1, A0. Run. Well, yeah. We take set spanning tree to contain one point. Let's say A0. Take point 1, A1. Now, the miraculous thing is that A1 you can choose the way you wish. You can choose it randomly or deterministically, doesn't matter at all. Randomly or deterministically. So you don't care. So you can toss a coin among all the points which remain, or you can choose the first one in some enumeration, or the one with the most beautiful name, or no one really cares. Then you run random walk from A1 till it hits spanning tree. So now what that means in our graph G is that we have spanning tree which contains so far one point. We have A1. We run random walk till it hits this point. Eventually it will hit with probability 1. Eventually it will hit. Do loop erasure. So we can just run loop erased random walk if you wish. Do loop erasure. So set spanning tree equal to spanning tree union with this loop erased random walk. So you add to your spanning tree, which had one point, the loop erasure of this guy. Okay. Now the next step is take A2 and then repeat as necessary. So we choose now point A2. We run the walk till it hits this aggregate. We add the loop erasure. Now we choose point A3. We run loop erased random walk till it hits the aggregate. We draw its loop erasure. We choose point A4. We run the loop erased random walk till it hits the aggregate. We add loop erasure. So at each step we get a tree. Because we have some tree, we take new point, run loop erased random walk till it hits, do loop erasure, so it adds one branch. So at each step we add one branch. And each time we add at least one vertex, usually more than one. So eventually we get all the vertices. And at most n steps where n is the number of vertices. So it goes very, very, very fast. So the theorem is that you get uniform spanning tree. You get all the spanning trees, and probability to get 2 are exactly the same. So it's so the theorem by Wilson theorem by David Wilson, we get all spanning trees with equal probability. So it's a very surprising and beautiful result. So the way I understand Wilson got, so it's kind of a bonus theorem to a more general theorem which tells you how to sample Markov chains very fast. It's called sampling from the past, and you can sample chains without having exact knowledge of transition probability. And it's sort of especially nice to explain in this case. Again, there are several proofs. Maybe later we'll do some. So as I said, immediately this first observation already means that the loop erased in the walk is symmetric. But also it says quite a lot about the spanning tree, because it means that if we want to estimate, for example, a probability that the branch goes through a given place, we need to estimate probability that loop erased random walks goes through a given place, which is related to random walk going through it, which is already something people are more comfortable with than uniform spanning tree. So it reduces many estimates to the estimates of a random walk. Okay. So now, before we go to a break, so what else did I want to do? Okay, so yeah, okay, so this is sort of an introduction. So the theorem which we want to prove, one half today and the other half next week. Yeah. So by the way, so the next, so there is, so we had next Friday was this Monday. So we didn't, we had lecture on Monday. We are not going to have it next Friday. So there are no lectures next week. So the next lectures are Monday, March 14th, Friday, March 18th, and let's maybe do one more Monday, because just in case, because then the random maps start and they might need some of the Fridays, so it's Monday, March 21st. And then actually there is an Easter break, I think. I think Easter break starts, then there is Easter break, and then we restart in April. And I'll first check with the Planar maps when, so how we coordinate the schedule. So it's probably like April 7 or something. Okay. So what are we going to prove is that uniform spanning trees and loop erased random walks are related to SLEs. But for that we need some sort of setup where you have Markov property, you have curves which go from A to B, and that we'll do after the break. So this is the setup we'll be working with. Take a simply connected domain omega, A, B belong to its boundary. I mean, for simplicity, we can assume that it's bounded by a nice smooth Jordan curve, but it's not really necessary because basically whatever, well, arbitrary domain in a sense works because we only need convergence of Dirichlet and Neumann problems, and they hold for wider class of domain. Then for epsilon positive, superimpose square lattice multiplied by epsilon. So what we do, we superimpose square lattice multiplied by epsilon. And take its intersection with the domain. With omega. Well, a priori, I mean, if you want to ask really boring questions, you can have, for some values of epsilon, you can get disconnected things, that there is a part of discrete domain here, which has two vertices, etc. So we just take the main component of it. So we get discrete domain omega epsilon with boundary point A epsilon, B epsilon, which are A and B shifted by at most epsilon. Then what we do, we add all the edges on the arc between A and B. So we take wire all the edges on A epsilon, B epsilon arc. So from A to B, counterclockwise. Consider UST with these boundary conditions. So people say that the boundary conditions for the uniform spanning tree are wired between A and B and free between B and A. So basically free we already have seen, it's no boundary condition at all, just consider all spanning trees. And wired means that we take only spanning trees which include this branch. Or you can say that it's a root, so it's a tree which grows on this, from this trunk. So we take only all USTs which include this arc A epsilon, B epsilon. So you get pictures which go something like this. So I'm not going to draw everything. Now we want to get a curve which goes from A to B. And what we do as a curve, we do a curve which goes around UST using the right-hand rule. Take, so we call it Peano curve. Peano curve goes from A epsilon to B epsilon along UST. So what is called right-hand rule. So this is how you're supposed to traverse labyrinths. Well, at least simply connected labyrinths. So essentially, let me just draw an example of how this would work. So suppose this is A, this is B, those are boundary data. So this is an example of a uniform spanning tree. So then we just start here a little bit outside A, and then we go. So this is the way this curve goes. So it's just like you are going inside the labyrinth using the right-hand rule, and eventually you will arrive to B, of course. You can also think about it in terms of the dual tree, because so as I said that for it, well, I draw it on on this picture that there is always a duo tree on the duo lattice. So there is a duo tree which is wired on the arc not AB but on the arc BA. So this curve goes between the tree and the duo tree. So basically this is the other way to look. It may be more logical that you can run uniform spanning tree wired on AB on our graph. Or you can write uniform spanning tree wired on BA on a dual graph. And there is a bijection between trees there and trees there, so which actually, it follows actually that the number is the same and probability is the same. And then if you have two trees, there is a unique curve which goes in between them. So it's kind of this yellow curve which goes between blue and white. Yes, yeah. So we get a random curve. So this is a random curve from A epsilon to B epsilon. So the theorem, which is Lawler, Schramm, Werner, and it's 2001. It says that as epsilon goes to 0, this piano curve, piano epsilon curve, goes to SLE 8. Now I have maybe to specify what exactly do I mean by curve going to a curve. If deterministic curve goes to deterministic curve, usually people mean Gromov-Hausdorff topology, so it's just the distance between the curves. For example, up to reparametrization, you take for a given parametrization of curves, you can take L infinity norm as the distance. Then if the curve without parametrization, you take the best L infinity norm of all reparametrizations. Now, so let's say so the distance between two curves which are parametrized, let's say gamma of t, delta of t, is equal to just supremum gamma of t minus delta of t over OT. Now the distance between two curves gamma delta is infimum of the distance above over all parametrizations. So if for example I have these two curves, then basically the distance is the size of this bump if I choose parametrizations properly. But of course if I choose improperly it can be bigger distance. So this gives me topology on curves, so this is the usual Hausdorff topology. Or then what I get, what is SLE 8 and piano epsilon are random curves. So random curves, what is a random curve? It's a measure on the space of curves. So it's probability measures on the space of curves with this topology, with Hausdorff topology. So this topological space on which I can denote, define Borel measures. So this is this means weak convergence in the space of measures on curves with Hausdorff topology. Or more or less, if you think of parametrization, you take space of continuous curves with L infinity norm, you take space of measures on those, and you take convergence. Now, the space of continuous functions with L infinity norm is not very good. but for all our purposes, you can think that our curves are Hölder continuous, and with probability 99%, they will have small Hölder norm, well bounded Hölder norm. So most of these measures, this and this, they live on a compact set. So it's actually, you can think that it's a measure on a compact set, except for very small crappy part, some small error, which is like 1% probability, and this is how usually such proofs goes, that you can work in a much nicer space. So is it clear what I mean by convergence? So it's the usual functional analysis convergence. So you have one probability measure, another probability measure, and probability measures converge. So making this stronger or weaker, I can by altering the topology on the space of curves. You can take Hausdorff topology, or you can take topology of Leibniz driving functions. So this is the theorem. So this should be understood. So if I had one curve which converges with just in Hausdorff norm, so there are parameterizations so that the supremum tends to 0. But here it converges in the sense of measures of curves with this parameterization, and it's the weak convergence. Now we'll do essentially the proof now, at least the main part of the proof, and the main part of the proof is to observe that there is something discrete analytic in the picture. So that was essentially known to Kirchhoff. So we'll do slightly different proof from Lowler, Schamann, Werner, and then next time we'll discuss their approach. So their approach is more via the Luprester and the Walk and the Poisson kernel. So we'll have something which is closer to Kirchhoff. So the first step is find a discrete analytic function. Okay, so what I'm going to do, I'm going to define two functions, and basically the first function, let me maybe take, draw again this graph. So there is this graph, there are points A epsilon, B epsilon, so I will just write A and B. So take point C on the arc BA. So we can take point C somewhere above. So C belongs to uniform spanning tree. So there is a unique branch from C which goes to BA. So there is a unique branch, let's say eta, from C to BA. So the picture goes something like that. And there are other branches in the tree, but there is this unique branch, so I denote it by eta. So now the function I'm going to look at is the, well, let's say u of z is the probability that z is right of eta. So for a point z, I look at the probability that it lies to the right of eta. Now, since it would be ambiguous to put z on my graph, because if it's exactly on the eta, is it right or left? So it makes more sense to define it on a dual graph. So define for z on dual graph. Probability, I mean in the space of uniform spanning trees. So probability in the UST space, so it's the probability is the number of USTs so that Z is right of eta divided by the total number of USTs. So it turns out that this function, and so this function is discrete harmonic, but it's easier not to prove this. One can just prove this, and essentially it was known to Kirchhoff. But it's easier to exhibit its harmonic conjugate and prove that together they are discrete analytic. So this, this function is defined on a dual lattice. And we'll define harmonic conjugate on our lattice. So that's the second function. Let me maybe erase this about the Easter break. So set a new function v of, well, let's say not z, but what are the other good letters? V of w. So this is on our lattice, And V of W is, so I will define it similarly. So it's number of WSTs. I will say in a second what that means, so that W belongs to the bottom. Now, what do I mean? So I now consider a slightly different model. I consider a forest which has two trees, and one tree is rooted here, and the other tree is rooted at point C. So I consider the following model, that there is a forest which has two trees, so one tree grows from C, and the other tree grows from the bottom. Yeah, so let me maybe draw it in a different color. So I have a uniform spanning forest of two trees. So I say that there is one tree which is rooted on the bottom and one tree rooted at C. So basically I take the same set of pictures as before, but only I chop it into two halves. And any such two tree forests are equally likely. Is it clear what is the model? But I normalize it the same way as the other way around, by just the number of USTs. So if you wanted to write it with the probabilities, it's equal to the probability in the WST thing that W belongs to the bottom tree. So this is, for example, when W belongs to the bottom tree. No, let's do W belongs to the top tree. Yeah, I like it more. No, let's think about tree which grows from above. That's like top tree. Top. Yeah, that will be. Otherwise, I get anti-analytic function, and I don't want to. But multiplied by the number of WSTs over the number of USTs. So the first function was probability, so it was between 0 and 1. But the second function, if you write it as a probability, you have to normalize by the number of these forests, not the number of trees. Now, well, so number of these WSTs. So it's actually probability, but with the coefficient number of WSTs compared to number of USTs. And this coefficient turns out that it tends to infinity. So it turns out that this function is eventually unbounded. Okay, so lemma, which is the key lemma, so lemma is that u plus iv is discrete holomorphic. So this function turns out to be discrete holomorphic. And also we can easily calculate its boundary values. Now let me prove this. Actually, there is an exercise 4. So you can actually prove that U is harmonic without using function V. So there is an alternative definition of U which doesn't appeal to left and right. You can also write alternative definition of U which doesn't appeal to left and right. This is what actually Kirchhoff does. So Kirchhoff considers similar function. It's related to conductances and or current running through the edges. And you can prove that it is harmonic without using harmonic conjugate. And the proof would work on any graph, not necessarily planar graph. Because if graph is three-dimensional, then you don't have harmonic conjugate because you don't live in a complex analysis realm anymore. So proof. So what do we need to show? We need to show that Cauchy-Riemann equations hold. We need to show that there is a complex derivative. We need to show that basically we need to show that if we have, for example, 2 points z1 and z2, so and we have two points w2 and w1. So we need to show. That v of w2 minus v of w1 is equal to u of z2 minus u of z1. So this was basically the definition of discrete analyticity. So that this difference is equal to that difference. Because basically what we are working with, we have imaginary part of our function which is defined on our lattice, and we have real part which is defined on the dual lattice. So together they form a square lattice in their own right. So it's it goes like this. And basically the Cauchy-Riemann equation is that for every square, this difference is equal to that difference times I. Times I is already, well, it's already built in because I write U plus IV. So basically this means that it's discrete analytic. Is it clear? Yeah. So in this case, we have a function on a square lattice which stores imaginary parts in one kind of vertices and real parts in another kind of vertices. Okay.
So you should have different sign on the horizontal edges, or just
No. We don't have. It's no. Everything is fine here on this picture because look. So in this picture there. No. What?
okay,
I think. Well, if I confuse the sign, then I just get anti-analytic function. So there is nothing crucial about it. But I think I'm quite right. I think I got the orientation of the plane correct this time. Okay. So the proof is just an easy piece of combinatorics. So let's start with for example, the bottom one, or maybe the top one. Yeah, let's start with the top one. or maybe the bottom one. I don't really want to know. So it's so what is the bottom one? So it's the difference that these 2 points, probabilities that these 2 points are left or right of curve eta. So if curve eta pass to the right of them, they both in one part. To the left, they're both in one part. So we have the same contribution to them. So the only really important case is if the curve eta goes in between. And it can go in between in 2 different ways. It can go so that Z2 is to the right, or it can wiggle around so that Z2 is to the left. And in one case it contributes 1, in another it contributes to -1. So basically this difference is equal to, so let me maybe write, probability that Z2 is right minus probability that Z1 is right, which can be written as probability of Z2 right, Z1 left, minus probability Z2 left, Z1 right, because if they are both right or both left, then it cancels out. And that I can draw graphically. So let me just draw this graphically. So this is basically, so the first one is, so Z2 right and Z1 left is configuration of this type. And the other one is a configuration of the type where the curve passes the other way around with a twist. So it separates them but passes the other way around. And then you count the number of such USTs, and then you divide by the total number of USTs. And now we do the most sort of straightforward thing one can try to do. We want, instead of these 2 points, Z1, Z2, consider points W, W1, W2. So what we do, we just erase this edge. And if we erase this edge, we get into a picture where you have a double forest, because you see this C belongs to 1/2 of this edge, of this curve, and B to the other one. So we erase this edge. And if I erase this edge, then I can rewrite the following, the very same thing. But now I count not the pictures with Z1 and Z2, but pictures with W1 and W2. In the first case, my point belongs to the tree from above. And in the second case, my point, top point belongs to the tree from below, and bottom point belongs from the tree to the above. So what I did, I just erased this edge, and that's it. So those are now these double forest configurations. So I still divide by the total number of USTs. But basically what I have now is divided by total number of USTs, number of double UST, so that, what is the point, W2 is in top and W1 is in bottom, minus number of WSTs, so that W2 is in bottom, W1 is in top.
now it seems like all of your WSTs, I mean, they never contain the edge from W1 to W2 if these are...
Yeah, because if they do, they contribute the same to... I mean,
if they do, they contribute the same thing to 2 points. It's the same, you see, I haven't made this step, so this is the step. When I make step comparing this probability and looking at the difference, I disregard all the configurations where this edge is, yeah. And there it's the same thing. So it's this important thing. It's what is this in probability? The difference of the probabilities of these two sets is also the difference of these two crescents. So this how it's called, Venn diagram, so Venn Euler diagram. I don't remember. There is some fancy word in school they use. So this is exactly 1 over the number of USTs and then the number of double USTs, so that W2 is top, minus number of double USTs, so that W1 is top. And this is exactly the difference of the other two functions. So Kirchhoff knew that these functions are harmonic. He uses a different proof. Maybe I'll put it in the homework assignment. So you can just write an analog of function u, just looking at the probability that you pass through an edge. So but basically, what is this function u? What actually we are looking at? We are looking at the probability. Let me maybe write it once more. We're looking at the probability that you pass through edge in one direction minus probability that you pass through the edge in the opposite direction. So Kirchhoff has shown that this probability is harmonic. So that's already in his book. And this is true in any dimension. You don't need harmonic conjugates. So we'll put this as an exercise. So there is another argument where you don't do harmonic conjugates. But with harmonic conjugates, it's in a sense much faster and much clearer. And the only sort of complicated thing is that we have probabilities on the left, but on the right, you see we have probabilities normalized by different space. So we have actually, yeah, maybe I'll write it one more time. So it's number of double forests over number of USTs, and minus probability W top minus probability W1 top. So it's if the first function is from 0 to 1, the second from 0 to 1 times something. Okay. Now we have discrete analytic function. We have to know boundary values, because otherwise they will be sort of useless. And the boundary values are quite easy. So it's, let me maybe just, so can I erase this proof? So the boundary values are, or maybe I'll just put it here better. So boundary values. So on arc A or on arc BC, our function u is equal to 1. So it's basically here u is equal to 1. Why? Because we are always to the right of eta. On arc CB, CA, u is equal to 0. So this is where u is equal to 0 because you are always to the left. And on arc AB, function v is equal to 0. So let me just put it different color. So v is equal to 0. And v is equal to 0, it's more or less the same thing as a Neumann boundary condition for Neumann boundary condition for u. So it's more or less says that the normal derivative of u is equal to 0. Why? Because what is the normal derivative of a function u? So the derivative of function u along the normal is equal by Cauchy-Riemann equation to derivative of function v along the boundary. And v is constant on the boundary, so u has normal derivative 0. So it's a very nice problem. It's a problem where u is bounded between 0 and 1, because the Neumann boundary part also gives you maximum principle. So that, have we discussed this already in exercise? It will be the next time. It will be the next time. So the next exercise series. Bless you. So this problem is approximately equal to the Dirichlet problem in the sense that difficulty is exactly the same. So for example, maximum principle you have because if you have normal derivative 0, you can't have maximum on the boundary. So maximum will be either on this boundary or on that. So function is between 0 and 1. And the key conclusion, so it's proposition. Proposition. As epsilon goes to 0, u epsilon plus iv epsilon converges to, let's say, f equal to u plus iv, solution of similar continuum problem. Now, what is the solution of continuous problem, which is 0 here, 1 here, and the imaginary part is 0 there? So what is the solution of a continuous problem that real part is equal to 0 on this arc, real part is equal to 1 on that arc, and imaginary part is equal to 0 on that arc? So you have something which maps this left arc to real particle 0. It's a vertical line. Real particle 1 is another vertical line. And imaginary particle 0, it's a horizontal line. So it maps it to half strip. So f maps to half strip. So is it clear? Because if I take analytic function which maps to half strip, obviously it exists because I can map to a disk and then I can write by hand what is a map to half strip. Then it will have real part 0 on this arc, real part 1 on that arc, and imaginary part 0 here. Now, if I have another solution, first I can use maximum principle to show that they are equal. But also I can use argument principle to show that they are equal, because if I have another solution, then every value will be taken exactly once, because when I go along the boundary, I will first go here, then I'll jump, then I go here, then I go here, so I will circle this point exactly once. So every solution of this boundary value problem is actually a conformal map, and the conformal map is unique because I fixed positions of 3 boundary points. So, so the exact thing how to address this problem will be in the homework assignment. Now, of course, I planned to deduce from this that we have an SLE 8 today, and I'm a bit slower than I thought, which maybe is a good thing. So we'll proceed next time. So it's Monday, March 14th, yeah, maybe it's bad because then we'll discuss at depth the SLE thing. But the idea as to what is next, so it's a small preview. So small preview. So what we do, we take subsequence so that piano epsilon j converges to some curve gamma. So for that we need some sort of precompactness. So we show that our curve piano epsilon, they are not completely crazy. Well, they are completely crazy because they are space filling, but they admit Hölder parameterizations, for example, so that we either will do it, or I'll just convince you that one can do it, because uniform spanning tree is related to loop erased random walk, so you can do different estimates. What is the probability that your branch goes through a given place, for example? Then we describe gamma by Loevner evolution, and then we run Loevner evolution while watching what goes on with U plus IV, while watching this map to half plane. And it allows us actually to determine that Loevner evolution is driven by Loevner evolution is driven by Brownian motion with a speed 8. And then we get that gamma is SLE 8. And since we did it for some subsequence, it will be true for every subsequence, so it will be true for convergence. So always true. So that's the preview for the next time. Now, what I want to finish today, so there are several ways to prove this proposition. So one will be in homework assignment, and it doesn't use uniform spanning tree at all. It just tells us that this problem converges to the other problem because you just address it in the same way as the usual Dirichlet problem. Now, you can actually here use uniform spanning tree also. For example, you can use it to do some priori estimate. For example, you can show that these functions are Hölder continuous by using uniform spanning tree. So what I mean by that, so suppose I have this discrete domain, and suppose I have 2 points at macroscopic distance. So it's not distance 1 lattice step, but it's some distance like A. And then what is the difference of values of function at these 2 points? It basically can be estimated as the probability that there is a tree which goes like this, minus the probability that it goes the other way around. But probability that the tree goes like that can be calculated by doing loop erased random walk, probability that loop erased random walk hits this thing of length A, which is smaller than probability that random walk hits it, which is smaller than, which is harmonic measure of this guy. So it's smaller than the size of the guy. So you can say that basically U of, if these 2 points are Z1, Z2, U of Z1 minus U of Z2 is smaller than probability of this, and you get that it's smaller than Z1 minus Z2 times some constant. So you get that actually Lipschitz property from if these points are away from the boundary. So it's basically there will be one proof in the homework assignment, but next time before we pass to SLE, maybe we'll discuss also the more probabilistic approach. So there is here an interplay. You can, once you reduce to this, you can work purely with complex analysis, no probability whatsoever. But sometimes it advantageous you can also work with the probability. You can prove this proposition using probabilistic arguments, not for UST, because for UST that's what we want to prove. But you can use probabilistic arguments for random walk, because you can write the same observables in terms of random walk, which is reflected on this part, and then prove it. Okay, so is it clear what is the observable? So it's clear that the thing is discrete analytic, yes? And then how SLE arises? SLE arises from the specific form of this discrete analytic thing. Okay, so no lecture next week because I'm away at a conference, and then the next lecture is on Monday, March 14th. Okay, and then there will be a long homework series because there is no lecture.